All right, so finally, I'm late to the class today, so that's also add to the delays. All right, so many of you know that homework 4 is due date is extended for the next Wednesday. So this is the last homework before your midterms. So concentrate on these 4 homeworks. 2 questions or 2 to 3 questions, long question will come from this homework. This homework. All 4 homework. I don't know exactly. Maybe it's midterms is 2 hours, so that means only 2 questions, 2 long questions, not 3. Final is 3 hours, so that means you have 3 questions. Okay, so that's so it's roughly 2 hours, but I give normally 3 hours to all of you to ensure that because you are taking these exams in take home, so I expect that there will be disturbance. You can't control that. So you'll get all of you get extra 1 hour, at least 3 hours. In class, if you take the same exam, you'll get 2 hours class time. Okay. And of course, there are other students who need extra time, for through CAE or other ways, then you ask for those time. And if you are already requested that through CAE, and you are already given for that time, so you don't have to ask multiple times. Okay, so where we are now. So week 5, based on the syllabus, we're supposed to finish drinking water treatments. So far, we're a little bit behind, but I really don't care, because ultimately at the end, by week 10, we'll finish everything. So it's not, so some of the things that is not part of the midterms will go become part of the final exams. Okay. So every final exam is not cumulative. So that means anything you cover in the midterms is not something you have to worry about in the finals. Okay. So everything we cover after this class will be part of the finals. Anything we cover until today is part of the midterms exams. Okay. All right. So one thing we did not finish last class is the groundwater extractions. What we learned at the end of this class, yes, on Monday, that you learn how to calculate the contaminant velocity in groundwater aquifer. So if you know what's the velocity of water, and if you know how much the pollutant adsorb on the systems, you can calculate retardation factor. Based on that, you can calculate how far a pollutants will migrate in aquifer. But a lot of times this is not really practical. All it says is how long you have before your well or groundwater well is going to be contaminated, right? So that's all you have. That's not a solution. That's just a pollution assessment, that you know that this is coming. Okay. So the real solution as an engineer is to really remove those pollutants, and the way it is removed is this extraction well. So imagine groundwater is moving these directions. Hold on. So this is. Okay, this is 1 second. You see that screen? Okay. All right. So as you see over here, the groundwater is moving in these directions. There could be potential pollutants, and your goal is to capture all those pollutants before it ended up in, let's say you have a drinking water well here. So this is your drinking water well, and you want to protect that well. You don't want the pollutants to reach there. So the way to do it is you draw another extraction well, which is here. So this one is extraction well. So your goal is to put extraction well before on the upstream, and pump so fast that all the contaminated water will draw into that well. So as you see over here, that's why it's called capture zone. That means if you pump at a certain rate, the what you see over here in this window, so this is basically the capture zone. That means this any streamline or groundwater coming through that window will all be captured within that extraction well. So that means any water over there will be pumped out. So the goal here is you pump all that water and treat them back and then inject back into the ground. That way everything upstream will be less contaminated. So this is a called pump and treat treatment systems that you will learn more about this system in next. There is one class on remediations in this particular CEE153, but there is an entire course on that which I teach next quarter. So that's all about designing this kind of remediation system. But point of this remediation system is how do you know where you put these wells and how many wells you need? For imagine that there is a all I'm based on this, if this groundwater moving these directions, you are not going to capture that because that's not within that window capture zone. So that means those polluted water will move along and then pollute other wells. So if your polluted water is over that, imagine there is a contaminated plume, and I will make this one as a contaminated plume. So this is your, let's say this is your contaminated plume. Contaminated plume. If this is the plume directions and this is the width of the plume, that capture well will or the extraction well will capture all the pollutants. But what if this pollutant is actually coming here? So if there are more and more pollutant plume above it, this extraction well is not sufficient to capture that. So that means what you need is you need another extraction well somewhere here. If you put another extraction well there, assuming you are pumping the same rate, it will capture over here. Okay. So that means using those two combination of two extraction well, you'll be able to capture the entire plume. So that's the design. So one of the problem is how many extraction well you need to capture certain plume, if you know the plume width. Okay. So that's the problem that you are going to solve in this one of the homework questions. So this is again contour to show that how the plume moves. So if you want to capture this plume, you have to put your extraction well here, assuming this is the direction of flow. So you may need one extraction well or you may need another extraction well. So let's say this is one extraction well, extraction zone, and this is another one, this is another one. So combination of all of them will capture something like this. Okay. Now question is, what determines that extraction range? How far the extraction locations? So that's all about, you are going to calculate now using a formula. Again, these are all mass balance equations. We don't need to derive anything because we already did it. All you have to do is remember what's the final formula for extraction well. So for instance, this is called cone of depressions. So what I saw over here is when you pump, this is, you're looking from the bird eye view, something that from the above. So that way you can see how the extraction or the plume is dispersed across the regions. But if you're looking from the side, imagine you can see the entire aquifer from one side, like this is aquifer and this is the well, there is a well here. When you pump water, it's more like a water will drop from other side. Because you are pumping so high to fill in that well, the water will slowly have inclinations. So that head will drop because we are pumping so high. And so that drop of head is something you can predict, because unless that head is different, water is not going to flow into that well from surrounding. Okay. So how far? So the question is, if you pump at certain rate, that well, the extraction, that cone of depression, what we call, because more like a cone, that depression will rise. If you pump so high, the cone will expand. That means you are going to draw water from farther and farther distance. Okay. And so those cones that over here, if you see, this region is where you can capture all water from. Okay, so any water coming through that regions will be captured. So that's the area where you can get most of the water from. So how far it is going to be? That radius will determine how much capture zone we will have. So how do you determine that radius of capture zone? Based on Darcy's law. So as you see over here, we start with Darcy's law. Q is the flow rate. This is the flow rate in that extraction well. K is hydraulic conductivity. Hydraulic conductivity. Area is, imagine this the well, right? So area is the well surface area. So that's the whole entire cylinder. And dH over dr. So dH is the drop in head. If you see over here, dH is the amount of head drop because of the pumping, and dr is the distance between 2 points radially, because the head is dropping radially, not one linear scale. So that's why, radius wise, you can go either way, the head will drop the same way because it's a cone. Okay. So that's basically, this is the hydraulic gradient, and this is in radial directions. Okay, because you are pumping at the center, water will drop from all directions same way. So now this is, as I said, area is the area of the well that receiving water from surrounding. So the height of basically the well area, if this is the well where water is coming into this from both ends, this height is basically the height of the well that is open to receive water. Because if you dig the entire well, doesn't mean that all the wall is for us. Only certain areas is for us to receive water. So that's the height where you can water can percolate through that wall. And this radius is radius of the well. So that's R. Now if you, so this is just the radius of the well. Imagine the cone. If you expand that cone in certain direction, how much water is moving into that cone is basically that radius is going to increase and height will remain the same. So that's why you put this height, area equal to 2 pi r, that's the circumference, and then HC. So if you substitute this one, then all you have to do is solve for H and R. So that means if you write these equations, what you got is dr is K, no, dr over r, because there is a r here, and the dr, if you take the other side, so dr over r is K 2 pi over Q times dH. So if you integrate this one, radius from one radius to, let's say, one radius to another radius, and if you know at that radius what is the height or the head of the water, H is so you are looking for what is the head of water at whatever that height is. So let's say at radius R1, the head, because of cone of depression, drop up to H1, and at radius R, the head is H2. When you solve this one, you have left side will be, so this one will be ln R, R1 to R2. H1 to H2. If you substitute all that, you get these equations. So again, this is unconfined aquifer equation. So anytime you are looking for this relationship between radius of influence or the cone of depressions and flow rate, this is for unconfined aquifer. So in your homework questions, always see whether this is given as a confined aquifer or unconfined, because that will change the type of equation you are going to use. This is only for unconfined aquifer, okay, because head is dropping and there is the width is, or the height of the cylinder where you are receiving water from, or the cone, is also changing. What if this is going to become a confined aquifer? So the difference between unconfined and confined aquifer is this, that no matter what the well is, all the well water has to move only on this side. Okay. It doesn't matter what well size is, no water will receive on the top, because water is only coming through that confined aquifer areas. So this width is constant, aquifer thickness is constant. That will determine how much water you can receive within that area. So as you see in these equations, before it was, this one was H. Here H, or the height of the well that receive water, is constant. That's the only difference. Before it was HC. Now we just substitute that equal to B, which is the width of confined aquifer, or thickness of confined aquifer. Or thickness. Thickness is a better word. That's basically this range B, because that's the only area you receive that water from. And this head over here is not necessarily inside the unconfined aquifer. This is just imaginary head. If you just draw a well there, how far the water will rise there. Okay. So this is just look like it's drawn on unconfined. That's not. It's just basically imagine you dig a hole here, and you'll see water depth over here. Okay. That's because in upstream, that's the head pressure over there. Okay, so if you solve these equations, again the same way, this become much easier to solve. On the left side, it will be dr over r is q by 2 pi k. Hold on, this is wrong. 2 pi b times k divided by q dhc. Again, R1 to R2, your head drop from H1 to H2. So same thing, ln R1 to R2 is same as 2 pi b k over q H1 S2 minus H1. So if you write these equations, only thing you have to worry about in your exams is this is the equations that you need to use if it is confined aquifer. And I forgot to mention that next week we have a quiz, week 6. That's your second quiz. And there are quiz questions on all lecture slides, example quiz questions. So that will be similar to those questions. Okay. And we'll have also some extra quiz question today. Okay. So everything we cover until today is going to be part of the next quiz. Okay. And that will also, quiz 1 and quiz 2 will help you prepare for the short question in the midterms exams, because you'll have 2 short 10 short questions. Each point is 2, where you will answer the questions either conceptually or using calculations. Either is fine, because it will ask, let's say for this one, if I have to ask these questions, I will say, if you increase the width of the confined aquifer, do we need to, how the radius of influence is going to change, okay, or how the cone of depression or the capture zone is going to change. So the cone of depression is basically radius, how the radius is changing with respect to, so if you put that other side, then you'll see a basic, then that's one way to look at. If you just see the numerically, whether it's a numerator or denominator, you can check whether it's increase or decrease. But other way to see is the conceptually. For instance, here, if you think of this, if you increase flow rate, what will happen to the radius? Just think of conceptually. You are just pumping water, right? Radius of influence or the cone of depression is a function of how far you can draw water from. So if you are pumping too fast, you can draw water from further distance because you apply that pressure, the head difference. So that's conceptually you can understand. So you don't need this equation to answer that questions. But if you put this equation, if you increase the Q value, how the radius is going to change. One of the radius is constant, so other radius is going to change best if you look at that equations. So another thing, if your hydraulic conductivity is increasing, how the radius of influence is going to change, or the pumping or the cone of depressions. So think of what is hydraulic conductivity. Hydraulic conductivity is the ability for water to move from one to another. So if you are pumping in a sand column, or let's say sandy beach, you are pumping water. If you pump water too quickly, you can draw water from long distance because they are all connected. Because hydraulic conductivity means how quickly you can draw water from farther distance. If it is moving very fast, that means you can influence those head over there. If the hydraulic conductivity is so small, even you are pumping, they are not communicating because it's so hard to draw, right? So if imagine you are drawing in a clay soil, even you are pumping, you try to pump so high, you'll pump dry because even you draw water from here, the water from here to here, it takes long time to come here. You pumped already, but this is not coming, okay? So if you increase so another way to say is if you increase Q, that's universally true, whatever, if you increase Q, your radius of the cone of depression or capture zone is going to increase. If you increase K, radius of capture zone is also going to increase. That means you can capture larger area. K is a function of aquifer. So that means if you are pumping in a sandy aquifer, that means you can capture a radius bigger flume. And why it is important? If you are trying to treat water, groundwater, it's a lot easier for you to clean up in a sandy aquifer because you can actually extract all the water as fast as possible. Yes. That's so depends on which one is used, but think of one way to R1 over R2 is the difference. So if you see this is what does that mean? Right? So this is basically a difference in radius. So it depends on which direction you are going, so that become positive or negative. So imagine you have difference in radius. What does that mean? How much you are going to capture? Like if you pump extra faster, how far the width is going to expand. So that's the same concept. So you can treat as a radius, just the radius. Okay. So what it means that if you are pumping at certain rate, how far that radius of capture zone is going to increase with your reference point. All right, so let's look at the example. This is a short questions, and this is exact same question as your homework. So let's see, as I said, this is just to plug the value and get the answer. There is no difference in this one. Suppose a well of 0.3 meter in diameter has been pumped at a rate of 6,000 meter cube per day, okay, cubic meter of day. So this is the flow rate. Every time you read a question, see what is that terms means. That way you can start writing those numbers. For a long enough time that the steady state condition apply. An observation well located 30 meters from the pumped well has been drawn down by 1 meter. So another thing that I didn't mention, what is drawdown means. So that's another thing you got to let me just mention here what's the difference, because it's not that different. So when you have a well here, this is the head, and imagine before even you start pumping, that this was the original head. Head means the water table height, okay? And if you are comparing from a datum here, so head is basically this. At this point, this part, this is the head, SW, or head in the well, okay? Or a lot of times people write H0 because that's the head at radius equal to 0, or whatever that radius of the well. And drawdown means how far that head has dropped because of pumping. So drawdown is basically original head minus the rest of it. So this is so S is original head before pumping minus the final head. So imagine this is I'm just going to write this one as your original head, H, before you start pumping, then S minus H. So if you know the original head, you can calculate drawdown or vice versa. Okay, so the drawdown is just the opposite of how much the head has dropped. Okay. All right, so let's solve the equations now, or the examples. So it says that at the observation well, the head has the drawdown is by 1 meter. So as you can see, what is the drawdown means? Over here, this is 1 meter. Means at this observation well, the head has dropped from this location to this, which is roughly 1 meter. Okay. And if you know the total height of the head, which is 30, that's the before you pump, then you can calculate what is the remaining head in that well. So that's 29 meters. So if the drawdown is given, you can always calculate what's the head. And your equation is about head, not the drawdown. Okay, so that's the only thing you have to think of. So at the observation well, let's say this is observation well, the drawdown is 1. So that means at that well, the height or the head at the observation well is 30 meter minus 1 meter, which is equal to 29 meter. So the head is given. Another well at 100 meter distance has a drawdown of 0.5 meters. So that means, so this is 30 meters. So that means this is R1 at radius from the pumping well. R1 is 30 meter. H1, so observation, you can write H1 is 29 meter. It depends which one you call 1 versus 2. It doesn't really matter as long as you follow the same things, you'll have the answer. And then the second well at 100 meters, so that means at the distance of 100 meters from the pumping well, so that radius 2 is 100 meter. The drawdown is 0.5. That S2 is 0.5 meter. That means H2 is the initial head minus the 0.5, so that's 29.5 meter. So R2, H2 is given. R1 is 30 meters H1 is hold on, this is 30 meters, H1 is 29 meter, Q is 6,000 meter cube per hour. And it says the well extend completely through an unconfined aquifer of 0.30 meter thick. That's the height of the original height. Okay, so that's the H original height. Before pumping, what's the head was. So determine the hydraulic conductivity. So all I ask is what is K value. And again, it says unconfined aquifer. So that's another thing. Unconfined aquifer. If it is unconfined aquifer, you just all you have to do is look for what's the equation for unconfined aquifer. So if you see the equation for unconfined aquifer, that's this. Q equal to pi K times H1 square minus H2 square divided by ln R1 by R2. So the K value, if you plug that value over there, K equal to Q ln R1 by R2. I'm just rearranging these equations. Then pi H1 square minus H2 square. Everything is given to you, so that all the value you can substitute to get the answers. Okay. And the answer will be, if you see, this is in meter per hour. Because whatever the flow rate is meter cube per hour, and the other one is in meter, so that means it's going to be meter per hour or day. What's the flow rate? Yes, meter per day. You're right. All right, the second question estimates the drawdown at the well. So it asks what is the drawdown at the well? How much this one is? So this is what the question is, what this value is. So to do that one, you have to think of that as a separate observation well. So another thing to see is, let's say this at the well, the drawdown is S0. Okay, I'm just showing what that number is. So that one is basically the initial height minus the head at the well. Right? And this is HW. Well, you can calculate head using the same equation that you just used. All you have to do is assume what is the radius for that well. So for that well, the radius of the well is how much? It says somewhere 0.3 meter, right? So that means that's the diameter. So that means this is 0.3 meter. So that means this one, the radius from here, from the center is 0.15 meter. So that means if you take all you are asking is from the center at certain radius, what will the head is? If you know what is the head, you know what is the drawdown. So if you write these equations, let's write these equations. I'm going to write it here. You know what is the K value. If I plug this value here, Q R well by R, let's say 2. All I'm doing is replacing one of the radius with a radius of well. That way you can calculate corresponding height of the head. Pi. Now H1 is become height of the head of the well minus. You just take different combination of radius and head. You know the K value from the previous questions. Radius of well is given, which is 0.15 meter. R2, just pick any of the other combinations. Now, whatever the head difference, if you put those values, you'll be able to solve for HW. If you solve for HW, you should be able to get that. So all you are doing is looking for what possible combination of H and R that you need to solve for the unknown. In this case, your combination is the well itself. And check other examples in the book so that you are familiar with this. And I can certainly say this is not a long question in the midterms because this is just very short. All you know is what is the questions and you just plug the value. This will be more like a short questions if ever I ask. Okay. And not like both. I will not ask both. I'll ask just one of them. Okay. Now, the last thing that you have to remember about this capture zone, as I said, how many wells will determine what is the width of the capture zone. And so if somebody asks, what's the net width of the capture zone, you will use these equations. Here, y is basically this. Y is the width of the capture zone. So that is basically this value. That's Q divided by 2 beta. This isn't for confined aquifer, just to. And there are two angles here. One phi is this angle, or phi, or what do you call phi probably? With these angles. If you want to know the entire width, what is the maximum width? When the phi, if you keep getting longer and longer, at one point, when phi equal to 0, that approximate to the infinity. So where the capture zone will be more likely. Imagine this is going around, that phi value is decreasing. So that means as it goes to the 0, that's where you basically at that point, you don't influence anything. So that approximations equal to 0, which is x equal to infinite, the value become this. So all you have to remember is this is the width of one extraction well. Okay. If you have one extraction well, this is the width. If you have two extraction well, what will be the width? That's basically another formula here. If you keep getting 2 and 2 and 3 and 4, the extraction well is going to increase. So for here, n equal to number of extraction well. So for instance, if n equal to 2, the width will be q over 2 beta v 2 minus 1 by 5. And if you think it's for infinite approximation phi equal to 0, then this value would be 0. That would be q over 2 b times 2. So it's q over. So that means if you take the 2 extraction well, the net width capture zone is roughly q over 2 q over b times v. Okay. So when you need it, anytime we ask what is the net width of capture zone, you just look for this formula. And in your homework question, it asks for two pumping well or 2 extraction well. Then you use this formula for the width. Okay. Really, you ask for to use for 3. Okay, so either 1 or 2. Again, these are the questions or these are the cheat sheet you need if you ever take the not PE exam, FE exam, Fundamental of Engineering exams. These questions mostly comes. Always you remember that equations. Okay. And here they will all just ask the simple question, calculate this value, and you just plug these numbers. FE exam questions are always very short, and you just need to know what equation to use. Okay, that's not really any complex questions. Basically, it will say there is a flow rate and there is the width, and this the everything is going to be given, and you are going to calculate what's the what is the width. Okay. All right. So that's all for the. Again, check this example question from your textbook. So this is all textbook textbook questions. So if you're not sure how to solve this question, just check this one before you do the homework questions. Homework question is exactly like this. There is no difference. So if you know how to solve the example questions, you should be able to solve the homework questions. Okay. All right. Any question? Oh, that's good. So I cannot see. Yeah. So the question was, what is the width in this Y? Yeah, that's basically the. Okay, I see what you mean. That's the width. There are two width here. One is the left side, another is the right side, right? So the right side width is if you go infinite far distance from, what is the width of that one? But near the well, this is the width that you are calculating is right near the well, because any water coming near the well is you are going to miss it. So imagine here, if there is a streamline coming here, this width is, you are not going to capture that water. So the width right near the well is what's the width we are calculating. But if somebody asks what's the width far away from infinite, that's the other width. Okay. Good question. All right, so I guess now time for 5 minutes sleep. You guys can sleep now for 5 minutes. We'll come back and change the topic. But when we come back, we'll have a quiz here, short quiz, so that you see how much you remember for groundwater. Okay, that's 3 questions here. Okay, we'll have that quiz. So let's meet at 1 o'clock in 7 minutes. All right, so let's have some example quiz. So the first question is, Darcy's velocity is higher than seepage velocity. Seepage velocity is actual velocity of water. So I'm saying is Darcy's velocity is greater than velocity of water. Is this true or false? Raise your hand if it is A. Raise your hand if it is B. So I didn't see any A. This is correct answers. The reason is, if you remember, Darcy's velocity is Darcy's velocity by porosity is velocity of water. Okay, this is porosity, and porosity is always less than 1. This value is always less than 1, because you are looking for how much fraction of the solid or soil is porous. It's not the entire soil will be porous. So 10%, 30%, 50% of the soil will be porous. The porosity is less than 1. So that means a certain fraction of velocity of water is actually Darcy's velocity. Or water velocity is much higher than water Darcy's velocity. Okay, next question. Which of the following factor would not directly affect the retardation factor? Retardation factor, if you remember equations, I'm going to write it. Bulk density, so that's bulk density times Kd divided by porosity, and Kd is fraction of organic carbon times affinity of organic carbons towards the pollutants. Okay, so raise your hand if it is answer A, B, C, many of you, D. All right, so as you can see over here, this is bulk density, fraction of organic carbon, that's FOC. Contaminant property is basically how strong the contaminant is binding to soil, that's KOC. The only thing that you don't have here is hydraulic head. Hydraulic head controls the speed at which contaminants, the water moves. It's nothing to do with retardation factor directly. Last questions. If you want to increase the capture zone width, which of the following factor would you like to change? So you want to increase, you want to draw down a lot more further areas. Increase the pumping rate, decrease the pumping rate, increase the pumping well diameters. Which one is obvious? Raise your hand if it is A. Some. Raise your hand if it is B. C. Okay, so if you see the capture zone width, which is just cover, is this. Okay. So obvious answer is flow rate. If you increase the pumping rate, you are going to capture much wider areas. If you increase the pumping well diameters, just increasing the well diameter doesn't change anything, because all it does is water is going to stay there. How quickly you can take them out of those areas is going to draw more water from surrounding. Okay, so the answer is A. All right, so that should be end of the everything that you need to know to do well in the midterms as well as the quiz next class. Not next class. Quiz will be on Wednesday. Okay. So again, same way, quiz will be released after the class, and you have 24 hours or until Thursday midnight to answer the quiz questions like you did last time. And quiz is also not cumulative. So that means everything that is part of the quiz 1 is not part of this quiz. Okay. So everything is covered after the last quiz is going to be part of these quiz questions. And you have many example quiz questions on the slide. So my suggestion is just to check the slide. If you don't understand something on the slides, try to understand that part reading the book. If you understand everything on the slide, you don't need to read the book to answer the quiz questions. For some reason, I forgot to turn on the sound, so I'm not sure in the chat window if everybody heard it. Nobody says, that means we probably they hear it. Okay, so next is water treatment. So everything from now is going to be part of the final exams. Okay. Because we are kind of late, so I don't want to rush this one into the midterms. Okay. All right, so let's look for how we treat water. This is In fact, 80% of the engineering problems, at least in environmental engineering problem initially, is all about making sure that everybody has equal access to drinking water. So biggest challenge is that still 1 in 4 people in the world do not have safe access to drinking water. Okay, so that's 25% of the world populations. That's many billions of people. And the reason you think of, now you're just going to learn about what are the different treatment systems. These are very basic. Still many people don't have that access. So even though this is very simple, we'll learn anybody can design some of these treatment systems. Still, it's not that easy for people in remote area to use that kind of treatment system, and we'll learn why it is the case. So one of the real world example, I don't know whether I have made you watch this movie or not. This is Flint water crisis. So basically how people in Flint, Michigan were drinking water contaminated with lead. And that's because they switch water from, instead of Michigan Lake, they switch into the river that has very corrosive water. Because corrosive water, the pH is low, it dissolves all the corroded pipes, and those corroded pipes has a lot of metals, including lead. So that's released into water systems, and that polluted the drinking water. So that's the reason the drinking water standards are there to monitor it. What's the concentration? So Safe Drinking Water is the first Drinking Water Act, 1974, just after EPA was established in 1970. They come up with this plan where they limit how much pollutants will be is permitted in drinking water. So that what it does, it allows any drinking water distribution agency to monitor their water system periodically, at least every day, to see if they are exceeding that limit or not. If not, they have to put new treatment systems. So this Drinking Water Treatment, the Water Act, determine what kind of treatment system you should have in your drinking water treatment areas. So there are primary standards and there are secondary standards. Primary standards is mostly enforceable. That's related to metals or pollutant that cause toxicity or certain known disease. Unenforceable guidelines related to smell. For instance, if you complain that my water is smelling bad, they don't have to enforce it. Now, it's just it causes customer dissatisfactions, but it's not really violating any particular case. So sometimes water smell, they say, okay, treat your own water using bleach or something. Whatever way you can do it. So there are certain things like taste, how they look, that might change from location to locations, but they care about pollutants. So these are the drinking water treatment standards, not many. You can see for different metals, different organic pollutants, many of these pollutants, and these are the standards. And it says what's the limit. Concentration, maximum concentration you are allowed to have. If it goes beyond it, obviously you are in violations. That means you have to see what kind of treatment system you have, how to improve it. So one of the things that you can see is that another problems that you come across is called maximum contaminant level goal. This is a maximum amount that you can have. That's not really, you can't force it because that fluctuates a lot. So just because you have something now doesn't mean it's going to change. So that's a different way how they manage it. That's a different all different class and policy how they manage this kind of level. So that one is the minimum contaminant or the maximum contaminant concentrations, but then there is also a level. You don't want to exceed that range. But anyway, this is just a quiz just to show that no, this is a MCLG is not enforceable. Okay. Just so that you remember that now this is something is not enforceable. Which one of the standard is enforced? This is the one, not the other one. Okay. All right. So the main point here now is how do you design drinking water treatment system? The first thing is where the drinking water comes from. Where they come from, that determine what kind of treatment system you'll have. In California, there are two sources of drinking water. One is groundwater, which is very small, because we don't have enough sufficient groundwater, particularly in LA. So that's very small quantity. The rest of the water coming from surface water. One is Colorado River, another is Northern California. All that reservoir you see from the water that comes from snow melt. So 90% of the water that we get mostly is surface water. And surface water and groundwater are very different things. For instance, if you have surface water, you might have more pathogens because it's exposed to atmosphere, so there will be board, poop, so a lot of things that can fall into it. And there could be high turbidity because it's moving on the surface, that maybe there are particulates. But if you pump from groundwater, you will not have many of those same characteristics. For instance, groundwater is rarely look unclean. It looks clean because it's moved through the soil, so soil filter out a lot of pollutants. So it normally doesn't look very turbid. But something else changed in groundwater because groundwater is moved through soil, so it dissolves a lot of salt from ground. For instance, if you are coming from Florida has lots of limestone. Okay, so when the limestone dissolves in groundwater, it changes the pH. It changes the amount of carbonate in it. That's one of the reasons you see limestone are very easy to dissolve. So you see a lot of sinkhole in Florida. The reason is dissolving that ground. Okay, and because of that, the carbonate concentration, so the things that makes it corrosive increases there, not corrosive or anti-corrosive. So based on where you are getting water, you can expect whether you have very high salt content or low salt content. If you are getting groundwater, it has lots of salt. If you are getting surface water, it may not have so much salt, but you may have lots of turbidity. Turbidity means a lot of small fine particles that you have to remove. So those things will determine what kind of treatment system you'll have. So again, I just want to say, groundwater usually have high salinity, high hardness. We'll talk about what is hardness. Hardness means more carbon, more calcium, magnesium, all these divalent ions. Because it's dissolved the rock, so you'll get a lot of this hard water. Hard water means if you take shower, this will not form any foam, and your skin will be like if it is hard water, you will see that after taking shower, your skin is very dry because all these very strong calcium, magnesium, they will kind of block the skin by forming a salt precipitate. So that means you can't take really good shower. Your shampoo will not work. Your hair will look like like as if it has a lot of glue. So you might experience that when you take shower in hard water, but here it's not because I would know. Okay, but hard water can be also bad for skin. So how do you treat those? So that depends on if you are taking groundwater, you have problem, mostly hard water problem. And how do you know if you have hard water or not? Just look at your faucet. If you look at your shower head will have lots of salt. It's build up of chalk or something like. It's like I don't know how to say this one. It's like a lot of gooey stuffs. And normally you don't find in LA because LA water is surface water, so it's not typically very hard water. So it's not a problem here. But if you go back to your home, which has mostly from groundwater, it might be an issue. And there are ways to treat it. So you learn that. So again, there are different ways to treat. There are different processes: physical, chemicals, biological. Physical means basically removing particles or turbidity. Okay. If it looks turbid, that means lots of fine particles. You are just removing that by filtrations or settling. Chemical treatment is basically using chemicals to treat certain type of pollutants. So chemical treatments are can remove obviously by adsorption. So adsorption is one of the treatments. Coagulations. We'll talk about this. What are those? Coagulation means if you have a lot of fine particles that cannot be settled, how do you remove them? That's coagulations or flocculations. And also disinfections. Disinfection, if you have lots of bacteria, how do you remove them? You can adsorb them. You can also coagulations, but they are not very effective in removing everything. So at the end, you add chlorine. Or you add some kind of disinfectant to kill those bacteria. So that's using chemicals. So that's the chemical processes. Then biological process, which is not very common in drinking water, but it is also very important in remote area where you don't have access to chemicals. You don't really get that expensive chemicals to do the treatments. You rely on biological process. Basically, you use biofilm to remove this is mostly natural way. Nature take care of things like this. Okay, nature also take care of things like physical methods. Chemical method is not very natural because really, nature doesn't produce chemicals to do stuff. We do use chemicals. Okay, so these two are natural methods. Okay, so this is just an example of every treatment system you can have. Okay, so let's see. Let's understand how it works. So you have surface water. First thing you want to do is surface water has lots of leaves, debris. It might have debris and all the stuff. So first thing is to filter them out. So that's why all these things, screen and grid chamber is basically a filter. It's like a strainer. Like in a kitchen, you can strain all your foods, so the water comes out. It's the same thing. So here you remove leaves, debris, large plastic, if there is any. Okay, so there you basically use the screen size. So that's the screen size determine how big the particles that can filter out. Usually these are very small because drinking water, you expect surface water to be clean. You are not treating something very dirty water. But if you do, obviously you have to use larger grid. So this is called filtrations. Okay. This will remove large particles, large floating particles. Okay. What it doesn't remove is anything smaller than the size of the screen. So that could be sand particles, that could be soil particles. They will not be removed because they are very small particles. So once it gets there, use sedimentations. Primary sedimentations, it means you have a big hole or big pond where you let the water sit for a while. If you let water sit for a while, all the large particles will settle. So now the clean water will be on the top, you remove those clean water. So that's called settling. So this is gravity. And this can remove anything, mostly medium size particles. So anything greater than 10 micron meter will be settled like this. Okay, any particles larger than 10 micron, obviously it has to be heavy too. It's not the size, because if you have 10 micron size of foam particles, it will never settle. Okay, because that's very light. So I'm assuming soil, anything mostly greater than 10 microns, or think of the size of hair. Hair size is 100 micron. So anything around that size will all settle out. Okay, anything smaller than that, less likely will settle. The next step is you remove all the large particles. Now things are very small that doesn't settle within the practical time frame. So something like bacteria or clay particles or less than 2 micrometer size, around that size, it takes more than 24 hours to settle, okay, or 24 hours or 48 hours. You don't have enough time to hold that much water, because you are, for Los Angeles, you have to, the amount of, it's 1 million of gallons of water per day that you have to supply. So you don't have space for storing that much water. So how do you control that? So you have to use some accelerated method or chemical method to make sure that they settle quickly. So that's coagulations. Coagulation, what it does is you have small particles. They are so suspending here and there. So you want to make them come together and become bigger and bigger. And as they become bigger, their size increases, they become heavier, they will fall down. So to allow that, that's process called coagulations. So how do you make coagulation? You add certain chemicals, which we did actually in the beginning of the class. In fact, next class, we'll have a demonstration for this treatment, so you can see how it works. So we'll add the coagulant, which is basically iron chloride. Last time we did it, and you see this is kind of red color, but this time we'll also show how to remove that red color, okay? So by adjusting pH. So we'll have next class demonstration on this method. I just want to explain this class theoretically this today. So coagulation is basically making particles stick with each other, become heavier, they will settle, okay? And so that's what happened is you add the coagulant dose, and then in the flocculation, basically they create this flock as they move together and find each other and create larger flock. Flock means large particles. As they become larger particles, they become heavier, and then it's easier to settle them down. So that's why you have a secondary sedimentation, which allow to settle the particles. So this is gravity. And this is adsorption. This is aggregations. So these are different processes that are important. So why adsorption takes place here? When you add coagulant, it changes the surface charge. Particles have the same surface charge, they don't stick because they repel each other. So you add a coagulant that alters that charge such a way that they will attract each other. So in fact, most of the natural particles are negatively charged. So the coagulant, the whole adsorption of coagulant is positive charge, Fe3 plus or aluminum 3 plus. So you add positive charge. So that means what it does, it removes that negative surface charge of particles. The moment you remove the negative charge, they don't experience any more repulsion. Now they can come close together and bind with each other because they don't have that repulsive force. That's the basic mechanism behind it. Once you have gone to this phase, you kind of remove every particle possible. Things that you don't remove is bacteria. Bacteria and dissolved pollutants. So those you can remove using filtrations. Filtration is basically you have a media where you add activated carbon or some materials that can bind this pollutant more strongly, dissolved pollutant. So this is also adsorption process. When you finish that one, now you remove all chemicals, or at least most chemical by adsorption. Every particulate pollutant, only thing that remains is some viruses or some bacteria. Because as you see, the drinking water standard for viruses or pathogens is very strict. You cannot have even a single pathogen in 1 liter of water. That's the drinking water standard, because one pathogen can cause you sick. If one bacteria diarrhea, the diarrhea bacteria, what is that called? Salmonella. If you have one salmonella, that can cause diarrhea. So that means you have to remove that one bacteria, even if it's there. So how do you do that? At this point, you add disinfectants. So disinfection is EV radiations. Sometimes people use EV light to disinfect. Sometimes people add chlorine, so dechlorination, so chlorinations or bleach. Once you add those, then you remove all pathogens. So only thing that you remove here is pathogens. And after doing that one, you add sometimes, because you cannot treat everything, so that the water is not necessarily, it's kind of corrosive, is not good for your teeth. So you add some fluoride. A lot of times you need to add fluoride before you distribute it. And then the distribution system, it goes to our home, and that's how we collect everything. And so this is the logical process of how you do things in a drinking water treatment system. So the quiz question, and not on this in this quiz, but in the following exams, we'll give a figure like this, and I'll move things around, and I'll say order it in the right way, so you know which one goes first. Okay, because you can't first, you have to remove the large one. Okay, if you put disinfectant, let's say here instead of here versus here, there is an issue, because you have so much particle and debris that you have to add so much disinfectant, because those disinfectant will absorb by those particles. So you want to have disinfectant when there is nothing left, only bacteria to kill. Because if you have any turbid water, that's going to absorb a lot of disinfectant. The efficiency will be much lower. So that's why disinfection is always at the end, because you don't want to waste your disinfectant. Yes, question? So adsorption is, we'll learn a lot more on the following slides, but adsorption is basically sticking up things on a filter media. And aggregation is basically a particular, if you have two particles, they come closer and become, it's like flocculations. So adsorption is more towards the dissolved pollutant, aggregation is particulate pollutants, okay, like bacteria or other things. We'll learn all that when we cover each of these mathematical way. So for each treatment, there is a math behind it. So we'll learn on how to calculate those. And the things that we'll cover most extensively, not filtrations, because screening is basically what size it is. So it's not really any calculations. You learn about sedimentations, you learn about flocculations, and then you learn about disinfections. So these are the three processes that you are going to learn in drinking water treatment class. That's the same process for wastewater treatment plant. Okay. All right. So now, as I said, I just explained the top one. That's for the surface water. But what if it is a groundwater? As I said, if you have groundwater, the biggest problem is not particulate. You will not have leaves and stuff in groundwater. They will not ended up there. So you will not have to worry about turbidity in groundwater. What you have to worry about is salt, dissolved salt. There are so much salt in, it's very salty. So you have to remove salt. Or you have a lot of hardness because of this excess ions. So as you see over here, things for groundwater, you don't have any of the screen or grid chambers, all that, because you don't have any particulates. In fact, you don't have turbidity, so you don't need a sedimentation tank because it doesn't have that much particle. Particle cannot move through ground. It's all filtered out very easily. So thing you directly go is to take care of the hardness. So this process, lime and soda ash is adding, that's to remove hardness. Okay, hardness is basically how much calcium, magnesium. So you have lots of calcium, magnesium, or I would say it's called hardness. The hardness is so high. So there is a definition of what that means. We'll learn that. Because so hard water, you want to soften it. So this is the softening process. Softening of water. Why it is important? If you have calcium, magnesium, your pipes is going to, scale will form, so your pipe becomes smaller and smaller. You will see sometimes the pipe clog inside so much, and that's because you have lots of hard water. And eventually, that's natural. There will be always some hardness. It's good for protections, because if you don't have little bit hardness, your pipe will corrode. That coating itself prevent corrosion. So you need to have some hardness, but if you have excess hardness, obviously it's bad. That it's going to scale. So that's why you need to soften the water. So that's something we are going to learn in the next week. And then once you create this hard water, this calcium, magnesium will precipitate as a salt. So you'll form lots of salt floating around. So you have to remove them by using sedimentation. So this is basically removing that calcium, magnesium carbonate. Calcium carbonate, magnesium carbonate, because you are adding soda ash, which is basically calcium hydroxide, you are precipitating them as calcium or magnesium carbonate. That's something you will see in the calculations. Once you remove everything, you, as I said, you need some amount of hardness because it protects prevent the corrosion to take place. So you have all this process. Then everything else is same. Okay. All right. So now that we cover this one, this is a short quiz questions in exam, final exam kind of questions. Why disinfection is carried out at the end, not at the beginning? I just already explained disinfection. The goal of disinfection is to remove pathogens. That means you want to add whatever disinfectant you want to add, you want them to directly attack the pathogens or bacteria. If anything else inside the water, they will absorb those. For instance, imagine if you have lots of particulates, turbid water. That's one of the reasons why in Flint, Michigan, not just they have lead contamination, a lot of people died because of Legionnaires disease. The reason is that Legionnaires, that bacteria grow inside those pipes. And when you add the disinfectant, now there are so turbid water because of those corrosion products, those disinfectants are not sufficient to kill them. So those bacteria, opportunist bacteria grow. So a lot of people become sick before even having the lead sickness. So that's the reason you don't want turbid water. You don't want even any dissolved pollutants, because if you have lots of organic, those organic will react with the disinfectant and form another disinfection byproduct, which can cause cancer. So in fact, that's one of the reasons if you take the tea, a lot of you drink green tea. Green tea is very good, right? But if you make it so hot in the microwave for a long time, they say that don't make it too hot. The reason is the radicals form, because any dissolved organic, so first the tea will release all the helpful chemicals which we need, caffeine and other things. But once they release, that's very quick. Within like very warm, small, little bit warm water, everything releases. But if you reheat them in microwave for a long time, I'm not talking about like 5 seconds or 1 minute. Let's say you really boil for a long time, particularly microwave, not boiling. Microwave can really produce radicals, because that organic is react with this high energy and produce radicals, and that radicals, although short-lived, they can also break down other organic and form specific organic chemicals, which is called disinfection byproduct, based on what else is there in your water, and form cancer-causing pollutant, particularly if you have lots of ammonium. So if your drinking water has lots of nitrogen, and you have these organic carbons, and you do disinfections, you are actually producing cancer-causing chemicals over there. So that was something not discovered before 1990s. People did all this treatment. They said this water is so clean, and there is no pollutants. And so they distributed, but then they found that there are these organic pollutants which can cause cancer are present. And they were not present before in the drinking water or the original source water. So they don't understand why their pollutants are here when it is not present the original water that get from surface water. Then they realize that the disinfection process is what causing that pollutant. So that's why they add the filtrations. This filtration is added to remove any dissolved organic. This one, dissolved. You want to remove them. So if you have dissolved organic plus nitrogen plus, let's say, UV light, cancer causing chemicals. So it's called disinfection. So one of our goal is to add that filtration to remove that organic layers. Okay, so that's kind of the background or the motivation behind this class, or what's the logic behind it. Everything else now we are going to cover is basically math explaining each terms and how to solve it. So it's already 1:40, so I don't want to start a new topic. So we can leave now. Okay, so all right, so next class we are going to learn more about the design. Okay. Let's see.